Today's lesson is about proportions in triangles. So this is a follow-up to our lesson on the similarity theorems in triangles. Today we're going to cover the side splitter theorem and its corollary, meaning a follow-up to that theorem. We're also going to be covering the triangle-midsegment theorem and the triangle-angle-bisector theorem. So let's take a look. Okay. So when we talk about proportionality in triangles, you're typically going to see diagrams that look like this, where you have two triangles that are overlapping each other. In this case, triangle ABE, the smaller triangle, is on top of triangle ACD. So if we want to determine the similarity between these triangles, it may be helpful to you, especially if you're a visual learner, to break apart or separate those triangles. So that's what I'm going to show you here. I'm going to take ABE and I'm going to move it over. So now you can see you have the total side lengths for triangle ACD and for ABE. So we can determine if these triangles are similar or not. It's not going to be possible to say these triangles are similar using the side similarity theorem because we don't have the third side. We don't know what BE is. We don't know what CD is. But what we can do, if I bring these triangles back together, is you can see that the triangles share angle A. They share angle A. They overlap at A. So we know that angle A, this is kind of a throwback to proofs here. We know angle A is congruent to angle A via the reflexive property. So angle A is congruent to angle A. And so now we need to use these side lengths that are given to us. We're going to try and prove that these triangles are similar via side angle side because we have two sides and one angle. So looking at side AC, if you add up the 10 and the 15, the total side length for AC is 25. If you add up AD, 8 plus 12 is 20. So when we set up a proportion here, we're going to determine if the ratio of AC to AB, so the left side of the bigger triangle compared to the left side of the smaller triangle, let's see if that ratio is proportional to the ratio of AD to AE. So let's fill that in here. We know that AC is 25, and we know AB is 10. So if you divide that, you would get 2.5. AD to AE, so AD is 20, and AE is 8. If you divide 20 by 8, you're also going to get 2.5. So we just proved that triangle ACD is similar to triangle ABE because angle A is congruent to angle A, and the ratios of AC to AB and AD to AE are the same. So triangle ACD is similar to triangle ABE due to side angle side similarity. So that was just a recap of last lesson. I just wanted to demonstrate that you will be seeing overlapping triangles more often than not today. Okay, so our first theorem here is called the side splitter theorem. This says that if you have one line that is parallel to one side of a triangle and it intersects the two sides, so we're talking about in this diagram on the right, MN is parallel to AC. If that is occurring, then MN is going to divide the sides of these triangles proportionally. So if MN is parallel to AC, then you know that AM to MB, so AM to MB, here's AM, and in a different color, we have MB. That's going to be proportional to the ratio of CN in orange here, to NB. And of course, when you're solving problems, you could set up these proportions in multiple ways. And I will demonstrate that with our next example here. So let's take a look down below. We want to find the value of y. We know that AM is 1, NC is 1.5, BN is 3. We are missing BM. We are missing the value of y. So to find that, we need to set up our proportion using the side splitter theorem. So I want to, before putting any values in, I just want to label my sides here. So I know that the ratio of AM to MB should be the same as CN to NB. So let's fill in what we know. We know that AM is 1. MB, we do not know that value yet. We're going to replace that with y. And then CN is 1.5. And NB is 3. So quick review of solving proportions. We need to cross multiply. So we are multiplying y and 1.5 together. And we're also multiplying 1 by 3. So when we cross multiply, you're going to get 1.5y equals 3. So now to solve for y, we divide both sides by 1.5. Cancel that out. And y equals 2. So that is the value of y. You'll notice that this works out perfectly because NC is actually half the length of BN here. 1.5 times 2 is 3. And you'll notice that AM is half the length of BM. 1 times 2 is 2, so it works out. So now I've got another example, and this one's a little bit more involved. We want to find in this diagram the value of x. So there is a lot going on here. So my visual brain is thinking, I want to take out the fluff. I'm going to take out the stuff I don't need. So I am going to, off to the side, I'm going to redraw triangle PQR the best I can. It's okay if it's not perfect. Okay. So you've got Q is up top, here's P, and here's R. So we are going to need this segment near the middle here. We know that ST is parallel to PR. That is important information. We cannot lose that. We're also going to keep Z here. And we're going to relabel what we need. So here, to find the value of SQ, I'm going to add SU and UQ. 4 plus 12 is 16. And to find the value of QT, I'm going to add QV and VT. 9 plus 3 is 12. So this is the bare bones information of what I need to solve for x. So using the side splitter theorem, I know that I know that QS, the ratio of QS to SP, should be the same as the ratio of QT to TR. I recommend setting up your proportions without the values first so you can make sure that you have the corresponding side lengths matched up correctly. So here we're going to fill in the information we know. So we know that QS is 16, SP is X plus 2, and then QT is 12, TR is X. So we need to solve for X. And again, we are going to cross multiply. So what you're going to get is 16 times X, which is 16X, is equal to 12 times X plus 2. It's important that we are multiplying everything in the expression X plus 2 by 12. Do not forget that step. Okay, from here we need to distribute the 12 into the parentheses. So we're going to get 16x equals 12x plus 24. Running out of room here, I'm going to move up a little farther here. 16x equals 12x plus 24. We need to combine the variables together. I'm going to move the 12x to the left side of my equal sign by canceling out on the right side, subtracting on the left side. So now I get 4x equals 24. To get x by itself, I'm going to divide both sides by 4. And I get x equals 6. To check your answer, to check that x really does equal 6, you can plug in the value of x into the proportion over on the far left here. So it would read 16 over 6, 16 over 8, my bad, is equal to 12 over 6. And that's true. 16 divided by 8 is 2. 12 divided by 6 is 2. That works out perfectly. In addition to the side splitter theorem, we have its corollary, which says if we have 3 or more parallel lines that intersect 2 transversals, then the segments are proportional. So in the diagram up at the top right here, we know that the ratio of AB to BC is equal to the ratio of DE to EF. So for example, looking at the bottom left here, I have some values for those segments, and I want to know what is the value of X. So we're going to set up the simple proportion again, just using the proportion given to us. AB to BC is equal to DE over EF. The ratios of these segments are proportional. So let's fill in what we know. AB is 7, BC is unknown, and then DE is 8, EF is 15. So now we just need to solve that proportion for X. We're going to cross multiply, so 8 times X is 8X, and 7 times 15. 7 times 15 is going to be 105. So now we need to divide both sides by 8. And here's my reminder to you that you are not always going to get whole numbers for your answers. Not all problems work that way. More often than not, you will be getting decimal answers. So when I divided 105 divided by 8, I got 13.125. And again, if you plug in that value for X in your proportion, it should work out just fine. So I've got an example based on the corollary to the side splitter theorem here. A reflecting pool is separated by walkways parallel to Lincoln Street and Jefferson Street, which are parallel to each other. The city wants to add additional tiling around the pool. How much tiling does X feet represent? So let's see here. How much tiling does X feet represent? So we're going to have to, again, take the ratios of the side lengths. I know that the ratio of this side, X, to this 60-foot segment here is going to be proportional to the corresponding sides. So the ratio of X feet to 60 feet is going to be equal to the ratio of 24 feet to 72 feet. So let's set up that proportion like so. And again, you could set this up in multiple ways. Okay, so again, we're going to multiply, cross multiply. So 72x, and then 24 times 60 is 1,440. Divide both sides by 72. And x is going to equal, I've got my calculator handy here, x is going to equal 20. So we know that the tiling on the X feet section of this diagram is going to be 20 feet. 20 feet. Our next theorem. And this one we use a little less often. This is the triangle-midsegment theorem. You might be familiar with the term midsegment when we talk about trapezoids. This is a similar thing. So if a segment joins the midpoints of two sides of a triangle, so we're talking about GH. GH is that segment we're talking about here. If you have a midsegment in a triangle and it bisects side DE, so DG and GE are the same length, and EH is the same length as HF, then we know that GH is parallel to the base of the triangle. GH is parallel to DF, and it's also half the length of DF. So just using a quick example here, I took that same diagram and I added a side length. If we know that GH in this diagram is 7.5, we can find DF using this triangle midsegment theorem. Because we know GH is half the length of DF, we're going to take that and multiply it by 2. Because we know DF is double that length. So 7.5 times 2 is 15. So we know that DF will be 15. On to a more nerdy example, I suppose. If you grew up playing Legend of Zelda games, you're probably very familiar with the Triforce. In yellow, you have an example of the Triforce, which is basically 4 equilateral triangles stacked together to create one bigger equilateral triangle. So let's say we know, all of the sides of these smaller triangles are 4 feet, right? They're 4 feet. What's cool is this segment in the middle. This is the midsegment. Let's call this triangle, for the sake of being fun, let's call it triangle high rule. High rules. High rule. Okay. So in triangle high rule, we know that the midsegment is segment YE. So we know that segment YE is the midsegment, which means it is half the length of segment RL at the base of the triforce. So let's label all the information we know. If these are equilateral triangles, we know that HE is also 4 feet. So is segment EL, because we bisected the sides of the bigger triangle here. So if those sides, or if the midsegment is 4 feet, then we know RL is going to be double that. It's 2 times 4. What's really cool is you can see if all of these triangles are the same, the base of this triangle, you have 1 as the midsegment. RL is the length of 2 triangle bases. So it works out pretty well. We're going to talk about angle bisectors now. We're going to switch gears a little bit here. So looking at this triangle, and the angle bisector is NL. You can see that NL is cutting angle KLM in half. So what's happening here is you don't have similar triangles. If you look at triangle NML and triangle KNL, they are not going to be similar. They first of all do not look similar, and not all of their side lengths are proportional. But we can examine the relationship between the side lengths here. So even though the triangles themselves are not similar, we know that the side lengths created by the bisector are proportional, which is pretty cool. And it leads us into the Triangle-Angle-Bisector theorem. So taking that apart really quick, you've got a ray in this diagram. Ray VX is bisecting this angle, angle UVW. It created 2 congruent angles here. So what this angle bisector did was it made the ratio of UX to WX proportional to the ratio of UV to WV. You could also write this proportion as UX over UV is the same as XW over VW. So it's pretty neat. So the ratio of these sides is proportional to the ratio of these sides here. So let's try a quick example. I want to find in the diagram in the bottom left the value of Z. So like before, I just want us to get into the habit of writing out the side lengths before we set up the proportions, just so we know we're setting things up correctly. So let's go like this. I want the ratio of WX to UX to be equal to the ratio of VW to VU. So I'm going to set up that proportion. WX is Z, UX is 28. And that's going to be equal to VW, which is 36, over VU, which is 32. So I'm going to multiply, cross multiply again. 32 times Z is equal to 28 times 36. So 28 times 36 is 1008. And so we are going to divide both sides by 32 to solve for Z. So Z is going to be 1008 divided by 32. and I get z equals 31.5. Here's another example. We are going to use the triangle-angle-bisector theorem to find the values of AD and DC. Find the values of AD and DC. So we need to set up a proportion again. This is where using the labels of the side lengths comes in handy instead of the actual lengths. So here's what my proportion is going to be. AB, the ratio of AB to AD is going to be equal to the ratio of CB to CD. Okay, so when we look at side AC of this large triangle, it might look a little confusing. That's why I wanted to set up our proportion this way first. So AB is 10. That one's pretty straightforward. AB is 10. AD is X. CB is 16. But now we have to deal with CD. So we know that AC, the whole left side of that triangle, is 13. So we know that if AC is 13 and AD is X, CD is going to be 13 minus X. You have to take away X to find CD. Okay, cross multiplying again, X times 16, you get 16X. And then we need to multiply 10 by the expression 13 minus X. So 10 times 13 minus X. So we're distributing the 10. 10 times 13 is 130. 10 times negative X is negative 10X. We're going to combine like terms here. I'm going to add 10x to both sides. So I get 26x equals 130. And I'm going to divide both sides by 26. So 130 divided by 26 is going to be 5. So x equals 5. But we were asked for the values of AD and AC. So if x equals 5, then AD is going to equal 5, because AD is x. DC, or CD, is 13 minus x. So it would be 13 minus 5, which is 8. So that means the sum of those sides adds up to 13. Our work works out. All right, and just a concept summary. The main theorems we learned about today were the side splitter theorem, the triangle midsegment theorem, and the triangle-angle-bisector theorem. Go ahead and pause if you need to take notes on those. Okay. So at the end of this lesson, you should be able to work on the practice problems for lesson 7.5. These are going to be due Mondays, so you've got a whole week. Monday's class and Thursday's class are going to be focused on your questions. I'm also going to be posting shorter concept-specific videos. So after you watch this video, you can go onto those if you need a quick refresher of one of the concepts. You can post in the office hours channel for public questions, and you can send an email if you have a more private question. Thanks for watching. Have a great day.